students, welcome back to the physics class. In the previous class, we already studied about how to draw the image formation of mirrors. I hope you all understood the content and you all drew the diagrams in your notebook. And today we are going to learn the rest of the chapter. So let's start today's class with the field of view of mirror. Children, do you know what is the field of view of a mirror? So let's have a look. The field of view of a mirror is the maximum range of the vision through the mirror. That means it is the area visible from the perspective of the observer through the mirror. Each mirror differs in their field of view just as they differ in the nature of images formed. That we already studied in the previous class. The field of view is maximum for a convex mirror. This is the reason for using convex mirrors as rear view mirrors. That means it has the wider field of view. So now you all understood that the convex mirrors are used as rear view mirrors. And from this we can understand that the mirrors are used in different occasions. So now we are going to study about which are the occasions we are using the mirrors according to its position of image and features. So let's have a look. First one, plane mirror, and we already know that in plane mirrors the image is formed behind the mirror and the distance to object and distance to image from the mirror are the same. The image is virtual, erect and is of the same size as that of the object, and the plane mirrors are used for observing the face. So next one, convex mirror. Here the image is always formed in between the pole of the mirror and the principal focus. The image is diminished, virtual and erect, and these types of mirrors are used as rear view mirrors that we already studied. Next we are going to study about concave mirrors which converges distant rays to the principal focus, and this type of mirrors are used in solar furnaces and in power plants. The next one is the concave mirror which reflects the rays coming from principal focus as parallel rays. This type of mirrors are used in searchlights. And the next one, if the object is placed between principal focus and pole of the concave mirror, the images formed are enlarged and erect, and these types of mirrors are used as shaving mirrors, mirrors in headlights of dental doctors, etc. So these are some of the situations making use of plane mirrors and spherical mirrors, and students try to find out more examples like this. Next one, we are going to study about the mirror equation. So for that, here you can see a concave mirror, and there is a question: should we draw a concave or convex mirror here? And the answer is the mirror equation works for both mirrors. So let's start with the concave mirror here, and you are already familiar with all of the symbols here. P is the pole, C is the center of curvature, and F is the focus, that is the principal focus of the mirror, and also here you can see the principal axis, and that is a straight line. And we want to mark the center of curvature, principal focus and pole on the principal axis. So place a object behind C at a finite distance from a mirror. We draw a usual diagram to get which is of course a real image here. So what is a mirror equation? So let me write it down first. That is 1 by F equals 1 by U plus 1 by V. It refers the distance between the points here. To understand better, let's draw a tangent at point P. Okay, and in this you can see U. U is the distance between the object and the mirror. This distance is the U. It is the distance between the points A and P. Remember, the distance between the two parallel lines always remains the same. Then V is the distance between the image and the mirror. So let's name this point as G. So V is nothing, the distance between image and the mirror Here you can see the image is formed at the point G, so that is the distance between G and P. Next one is here. F is the distance between the principal focus and the pole, and this distance is equal to the principal focus. And here you can see all of the distances are measured from the pole P of the mirror. So from the equation you can see that it gives us the relation between the object's distance from the mirror, image distance from the mirror and the focal length. So what if instead of this I have placed the object somewhere else? It wouldn't change the formula. That means the mirror formula does not depend on the position of the object. So what if we are using convex mirror instead of concave mirror? Here also the mirror formula remains the same. That means it does not depend on the mirror used. So for the convex mirror and the concave mirror, the mirror formula remains the same. That is 1 by F equals 1 by U plus 1 by V. Next one, focal length. Do you know what is focal length? That we already studied in our 8th standard. Focal length is the distance between center of the mirror and the principal focus. And the equation for finding focal length is F equals UV divided by U plus V. And on rearranging the expression F equals UV by U plus V, we get the mirror formula. That means we get the mirror formula from the equation of focal length. That is F equals UV by U plus V. So students, that's about today. Learn the topics well. See you in the next video. Thank you for watching.